So our speaker today, Charles Brown, works at the interface of experimental AMO and condensed matter physics. He's currently a Ford Foundation postdoctoral fellow at the University of California, Berkeley. He did his doctoral work at Yale, and he has a BS, as he just told us, from the University of Minnesota. Charles has worked on two of the coolest experimental systems, literally. At Yale, he did experiments that demonstrated for the first time optomechanical coupling between electromagnetic cavity modes and superfluid helium phonons, measuring Brillouin scattering at the few phonon level and 0-point fluctuations. This work was reported in Nature Physics and PRL and was featured on the APS website spotlighting exceptional research. At Berkeley, he's done some interesting work on cold atom gases trapped in an optical Cogamine lattice. And this is the work he's here to tell us about today. As a graduate student, Charles served on the board of the National Society of Black Physicists. He was one of the organizers of Black in Physics Week last fall, which aimed to increase visibility and recognition of Black physicists and their contributions to physics, and also to provide a community of collaboration and support for Black physicists worldwide. He's the author of an important commentary in Physics Today, which everyone should read. So welcome, Charles. The floor is yours.
Thank you. Thank you for a really, really great introduction. And I really appreciate that you all invited me to speak with you today. Let me share my screen. There we go. Okay. Great. Yes. So as Sarge mentioned to you, I will tell you about the work I've been doing over the last year and a half as a postdoc. In particular, I'll describe a couple instances of non-equilibrium phenomena of ultra-cold quantum gases trapped in optical lattice potentials. All right. And so throughout this talk, I wanted to make this as accessible as possible for the largest number of our audience members. So I think for the experts, I will review some things you were familiar with, but I really hope that everyone can learn something from what I present today. So first, I just want to define lattices. A lattice is a periodic set of points that has some set of symmetries. There we go. Okay. For example, the square lattice, it has a sort of translational symmetry. As you see, when you move this way or this way, the lattice looks the same. It also has a rotational symmetry. If you rotate the square lattice by 90 degrees, it also looks the same. Here is a triangular lattice, also has some sort of translation symmetry, has a different rotational symmetry, 60 degrees instead of 90. Or the lattice that's most near and dear to our hearts in the Stanford Kern group at Berkeley is the Cogamine Lattice, a sort of triangular lattice that also has the same 60-degree rotation symmetry, and some sort of translation symmetry, right? And common to physics of particles on a lattice is this idea of band structure, that is, the energy of particles in the lattice versus their in-lattice momentum. That's what this Q is. So what I'm plotting here is the energy of particles in the lattice versus their in-lattice momentum in two cases. One case where technically there is no lattice, so the lattice depth, the strength of confining particles to the lattice points is 0, versus a case where that confinement is non-zero. And so when the lattice is off, you have the relationship between energy and momentum that you expect. You expect something like p squared, or in this case, q squared over 2m. And so you see a series of parabolas that correspond to available energies. Whereas in the case where you actually turn up the lattice depth, you turn up the confinement of the particles to the points, then you have these gaps that emerge, the white spaces here, where particles are no longer allowed to have energies within those ranges. So the particles might have energies that exist in this band, or this band, or this band. So as it turns out, a solid's band structure describes the allowable energy levels for electrons in a crystal lattice. And in these cold atom experiments, what we're typically trying to do is to build an analog system a system that can sort of replicate the physics of, as well as we can, electrons hopping around in a solid crystal. Okay. So band structure explains material properties like electrical resistivity, Hall effects, spin, quantum, etc. Hall effects, optical absorption, orbital magnetism, topological insulators, lots of other things. And you typically describe these, you typically describe the particles in the lattice with some block wave function, which looks like some periodic function u multiplied by a phase that depends on the in-lattice momentum. And like I mentioned, this u is periodic. You have this really important boundary condition that the function u at a location that is one lattice vector away, so sort of one spot away on the lattice, has to be the same. Okay. So I want to also mention frustration before I get into how it's relevant for us, geometric frustration specifically. So I like to define this as conflicting interatomic forces that make unclear the lowest energy state of a system. And one really nice way to think about this is a system that has magnetic frustration. And you can think about this just using 3 particles. So imagine that I have 3 particles that have spin. Their interaction is antiferromagnetic, so they want to be anti-aligned. If you then imagine that I put a spin up on this side of the triangle and a spin down here, then the question is, that shouldn't have advanced, but the question is, what should be the state of the spin, up or down, on the top portion of the triangle, if the goal is to minimize the energy of the system? If I make the top spin up, or if I make it spin down, you'll see that one pair of spins has an up-up alignment versus the other one having an up-down. And so it's unclear what is the lowest energy state of the system. But for us, our goal is not to study magnetic frustration. It's to study frustration associated with motion. So our goal is to study the physics of orbital frustration and how it leads to exotic states of matter. That's sort of the pie in the sky goal. And our method is by creating we do this by creating a Bose-Einstein condensate, and we put it in a lattice that causes orbital frustration. That is the Cogamine lattice that I'm depicting here. And there are a number of physical states you might try to measure, or different kinds of phenomena that you might try to observe. A few that I've listed here, some special superfluid state called a trion superfluid, or supersolids, various forms of topological matter, superconductivity, interesting forms of magnetism. And I just wanted to point out something that I think is pretty special and I'd like to look out for. There's a PRL paper that came out about the superfluidity of bosons in the Cogamine lattice. And this gets to an open question about what bosons do in a flat energy band. All right, we typically imagine that bosons will condense into the lowest available energy state, but what happens when your energy energy band doesn't have a clear minimum? And so in this work, so let me just say this. I'm showing more band structure, so band energy versus quasi-momentum. And it turns out that given interactions in the flat band, you take what was initially a flat band and you develop minima, specifically at gamma and k, quasi-momentum. And this corresponds to the formation of a new state, a new superfluid state that is, I guess, described by this correlation operator. It's this is the fact that these operators appear up to the 3rd power. This is where the namesake trion superfluid comes from. And it turns out that at much higher temperatures than you have a normal superfluid, described by this operator, at much higher temperatures, you have a sort of quasi long range order triple boson paired superfluid. So just a really interesting state of matter that has been sort of elusive, and you know, a Cogamine lattice is an interesting system to see this in. Okay, so the Cogamine lattice isn't the only frustrated lattice. This is the Cogamine lattice. It's characterized by a 3-site unit cell, I'm calling A, B, and C, and some hopping energy J that corresponds, that describes particles hopping from lattice site to lattice site. Another frustrated lattice is the Lieb lattice, for example. It's a square lattice, also 3 sites, also has some energy J. And common to both of these lattices are interesting band structure. So in the Lieb lattice, there's a flat energy band, and this is what we are really interested in. But there's also other interesting points. So for example, these points here, these are Dirac points, where the energy dispersion between the bands is linear. And this, I guess, physics around these points is sort of similar to the physics of electrons and graphene near the Dirac points.
Sorry to interrupt you. Charles, I saw that how the magnetic frustration works on a Kagamine lattice, but what does the orbital frustration mean?
So when I say orbital frustration, actually, that's on my next slide. Okay. So let me get to the next slide. Thanks for asking that. But yeah, so also in the Cogamine lattice, there's a flat band. Unfortunately, it's the highest band, and that makes some problems for us, but that's okay. And there's a series of interesting points, Dirac points, Van Hove singularities, et cetera. And for the physics that I'm going to describe in this talk today, I just want to mention that these authors here see a sort of similar effect in their Lieb lattice, and an interaction-driven change in the band structure that gets to this question about what bosons do in a flat band. Okay. So to your question, when I mention orbital frustration in the Cogamine lattice, I'm talking about I'm referring to the atomic motion, and I'm talking about there being a large number of states of the system which are available states for the atoms. So yeah, we are not looking at magnetic frustration. This is a situation where we have a bunch of atoms in this flat band with the same kinetic energy. Right. So not only is there physics to study of the variety that I described before, but even when you consider larger areas in the lattice, larger than a single unit cell, you can even have interesting states of vorticity that can pop up from the fact that you can have an oscillating phase of the atoms at different sites, and the velocity is given by the gradient of the phase. So you can have multi-site vorticity, and this is something I'm interested in from my work at superfluid helium. But I just wanted to lastly show this band structure. So right here, I've plotted for you the band energies versus in lattice momentum of the first 4 bands of the Cogamine lattice. So this is the first band, second band, third band, fourth band. And I wanted to point out here that this is the flat band. So we want to load Bose-condensed atoms into this band and observe what happens. That's the goal. That's what I will eventually show you measurements for.
So Charles, just a quick clarificatory question. The band structure you showed, it's not a tight binding model then, because you've got 4 bands. So you've actually assumed some potential with the Kagome periodicity.
Yep.
Okay. I see. So the flatness I assume is not ultimately if you make the potential change, the flatness would go away. So, but I guess this is deep enough that it's flat, you're saying?
Yeah, it is.
Okay. Yeah. All right, great, thanks.
So just to another clarification. So does it depend on whether you include more than first nearest neighbor, second nearest neighbor, and so on interactions, whether it stays flat, or does it become not exactly flat if you include longer range interactions?
That's a good question. I don't know the answer to that question. Think about long range interactions.
Yeah.
I'm trying to think of some work I'm familiar with. I haven't looked at it myself. I'm trying to think if I've read anything about this. So this picture is definitely not in consideration of anything other than contact interactions. I don't know. Let me think about this, and maybe we can come back to this a bit later.
Sure. Thank you.
Okay, so how do we actually do some of these things in the lab? How do we develop an optical lattice potential or optical lattice? Well, so we use these traveling waves that happen to be lasers. Mathematically, it looks like two counterpropagating traveling waves, the blue and the red. And when you look at their interference, you get this black standing wave. And as I mentioned, we can do this in the lab by sending two counterpropagating lasers to overlap with each other. And if you look at the intersection, and you look at the time average electric field intensity, what you get is a standing pattern that looks like this, where in the potential minima, I can load my atoms. And I can extend this process to by using multiple pairs of beams or overlapping multiple pairs of beams to make a two-dimensional or three-dimensional lattice at my discretion. So for us to build an optical Kagamine lattice, we actually use 6 lasers. 3 of them are sort of paired up in a particular way. And really what we effectively do is add a triangular lattice on top of a hexagonal lattice in just the right way to make a Kagamine lattice. So we take one set of green laser beams, and this really is green, it's 532 nanometers, and we overlap them in a plane with a relative angle of 120 degrees. And then we basically make a replica of that resulting lattice, but we do it with infrared light. That's what the red is, at double the wavelength. So 1064 nanometers, and we overlap them very precisely. And if you look at the potential energy landscape that the atoms experience in this overlap region, it looks like this. And this is the Cogamine lattice, your vertex sharing equilateral triangles that exist in this arrangement. So this is my Kagamine lattice. So let me actually get into the measurements. To do this, I've told you about how we make our Kagamine lattice. What we're going to do is make a BEC, and then we're going to load the atoms into that lattice. To actually get the atoms into the flat band, we first make the BEC. This is my BEC here. And then we use a laser to give the BEC a kick. So this is a dipole force that we can apply to the BEC to give it some quasi-momentum before we ramp up the lattice. In doing so, we're able to load the atoms directly into the third band, the flat band, the should-be flat band, at quasi-momentum that's associated with the real space momentum we gave it by kicking the BEC with the laser. In order to look at the band structure, this is what we're interested in. What does the band structure do? We look at what we call diffraction images of the BEC and the lattice. So what I'm showing you here are predictions for these diffraction images or momentum space images of the block states. And here are our experimental observations of these momentum space descriptions of the atoms in the lattice. So what you can see here in these first 2 panels are atoms in the first band. This is with 0 momentum, so this is at gamma. This is with a non-zero momentum. This is atoms in the third band, and this is atoms in the fourth band. So one thing that we know is that with this technique, we can do a decent job of loading atoms to some non-zero quasi-momentum in the lattice. And we know that we can put them into a particular band. Okay. Now we can take these images, these momentum space images, and extract some really useful information from them regarding the band structure. And that we're able to do this because of this very general result from quantum mechanics, the Hellman-Feynman theorem. So just regardless of interactions, we're able to relate the group velocity of the atoms to the slope of the band energies. Now, the group velocity, we can just find from looking at the center of mass or the center of intensity of these images. So what we do is we load the atoms to some quasi-momentum into some band. We take momentum space images in this way, and we calculate the center of mass. That is a direct measurement of the group velocity, which is a measurement of the slope of the energy bands. And so here I'm plotting the slope of the energy bands. versus quasi-momentum. The data is blue. The dashed lines is the non-interacting band theory, and then the solid lines are the Gross-Patevsky equation solved in the lattice. So we see in the first band, our data agrees pretty well with actually sort of both pictures, but in particular, the data agrees better with the lattice Gross-Patevsky solution as opposed to the non-interacting band theory. Maybe the same is true in the fourth band, but here's where your attention should be. This is where the flat band is. This would be flat. It depends on in this non-interacting picture, the lattice depth, as Harsh was bringing up earlier. But if you notice here, the data that we've collected agree somewhat okay, I would say, with the picture that includes interactions, so the Gross-Patevsky equation solved in the lattice, and doesn't agree particularly well with the non-interacting band theory. Right, so this is already some sign that the fact that atoms are interacting with each other has somehow changed the band structure, moved away from this flat picture that we might expect. Okay, and so as I just mentioned, the interactions between the atoms are restructuring the optical lattice in some self-consistent way. I think some people refer to this as band structure renormalization. And it turns out that because of the significance of the interaction part of the Gross-Patevsky equation, the atoms effectively see a new lattice that doesn't quite look like the Kagamine lattice. And so perhaps for that reason, you might expect to move away from this flat band picture, or to develop a new band structure that no longer has this flat band. Now, there are several interesting effects to study with this, in particular nonlinear block theory, where interactions change bands. And I realize that band structure is a non-interacting physics picture, a single particle physics picture, but nevertheless, when you do have interactions, you can open up what people call swallowtails in band structure, or have bands that bifurcate. And so you might imagine that if you have the ability to move through quasi-momentum in a particular direction, you might end up in a situation where you can move atoms along one band, and then all of a sudden the band just disappears. Your atoms have to fall into another band, and that whole process can become complicated and interesting, I think. Okay, but enough about that. I want to tell you about a few more measurements, just to sort of verify or make a stronger point that the band structure is being changed by the interactions. Here's a plot of the group velocity, or the slope of the energy bands, versus the strength of the lattice. Here, then this is in the third band. Again, our data agree much better with the Gross-Patevsky equation, where interactions matter, and those interactions being affected by the lattice depth, as opposed to the dashed line that tells us about non-interacting band theory. Or perhaps the most clear, we plot the slope of the energy band versus the peak density of the BEC before we load the BEC into the lattice. So this isn't a direct measurement of the in-lattice momentum, but density, but certainly the in-lattice density does increase with the peak density of the BEC. And so we see that the data follows this nice trend that goes along with the lattice Gross-Patevsky equation. And we see that the curvature of the third band has changed more and more as we increase the density. So this is coming from the interactions. Okay, so lastly, this is the last thing I wanted to say about the Kagamine picture before I move on to the next topic. So here is an expectation of the site population, I guess the amount of atoms in each side of the Kagamine lattice. And here my sites are labeled in this way. And so again, the dashed line is non-interacting band theory. The solid line is the lattice Gross-Patevsky equation. And I guess the thing I want to point your attention to is, as I move to the right, I'm increasing the depth of the Kagamine lattice. And in doing so, you can see you can see one primary difference between the two cases, and that is looking at the population of atoms, say in this region and in this region, which is the lattice depth where we collect most of our measurements. In these regions, you see that the population of atoms, they're dispersed in a different way across the different sites of the unit cell. And so when we have our kind of full depth Cogamine lattice that we use, given the interactions, what we see is a lattice that doesn't quite look like a Cogamine lattice, but more like a 1D stripe lattice, a stripe lattice, where primarily the atoms are in sites C and B here, and there's a little bit in A. And so again, this is an example of the interactions effectively restructuring the lattice. And this is something that you would be able to see in a real space image. This is a simulation, but if we had, single site resolution, say we had a quantum gas microscope, this is a real effect that you should see, the lattice geometry changing effectively as a result of the interactions. Okay, so this is where I wanted to stop for the Cogamine project. I'm going to talk about something different. Maybe now would be a good time for a question, or people can wait till later if they would like.
Sure, I think I'm going to hold off till the end, but if anybody else wants to ask a quick question now is a good moment.
I wanted to ask, sorry, I'll turn on video, was when you're turning on the BEC first and then adding the lattice on top of that.
Yep.
So do you have the option, you can populate however many atoms per unit cell as you want. Is that, am I understanding that right?
We don't have very good control over that.
Okay.
So the number of atoms per site is of order tens.
Okay.
But whether that's 20 or 70, we don't really have that kind of control.
Okay. And is that where I was somehow, when I hear about this, I was picturing one per site, but do you ever do stuff like one?
We don't. We would love to be able to, but we don't. So yeah, it's definitely tens of atoms per site.
Okay, thank you.
Okay, well, maybe I will move on to the next topic. We can talk more about Cogamine lattice stuff if people would like to later. Okay, so I already mentioned that a solid's band structure describes the allowable energy levels. I told you about different sort of phenomena or properties that come about because of this band structure, but I left out the fact that not only does the band structure matter, what also matters is the geometry and topology of the state space, of the Hilbert space, where the wave functions live, or the block wave functions live. So not only do you care about these block wave functions, but you also care about things like Berry connection, or in special cases, one of which I think is ours, a degenerate analog of Berry connection, the Wilczek Z connection, where now you're thinking about evolution between a degenerate manifold of states. But nevertheless, some kind of Berry connection or Wilczek Z connection where you can have interband transitions, for example, because of geometry. Okay. And so just as a little introduction to what I'm going to talk about, I'm going to talk about physics of Dirac points. And so I want to talk about singular band touching. So a band degeneracy or a band touching point is caused by some set of symmetry, and a singularity at a touching point is caused by or associated with a block state discontinuity. Okay. Singularities occur in some flat band models. These generally have non-trivial origin and consequences. This comes from some sort of interference effect associated with different pathways of particles hopping to different sites and how those processes interfere. And it turns out that because of a process, maybe I shouldn't call it process, but a phenomenon that arises associated with what people call like compact localized states. These are almost like the, I'm forgetting what it's called. Okay, for some reason I kind of just drew a blank, but anyway, you get these interesting localized states in real space that arise in some interesting physics. I'll say it that way. And there are a number of papers that I would recommend for people to check out. Maybe in particular this paper that just came out last year, where the authors describe a process by which Landau levels split in a very particular way due to a singular point in a system with a flat band. So the authors describe an anomalous Landau level splitting because of some flat band physics that depends on only a geometric property of the Hilbert space, something that people refer to as the quantum distance. It's the Hilbert-Schmidt distance in the Hilbert space. Okay, so the singularities, they don't only happen in, of course, the Cogamine lattice. They also happen in the Lieb lattice, a dice lattice, which is another lattice that has frustration. It has flat band, or even the honeycomb lattice, a simple lattice. This is effectively graphene. And a notable example of such a singular point are the Dirac points in the graphene lattice or honeycomb lattice. And in this picture, people often will think about this as sort of the band population between the first two bands being sort of like a pseudo spin in a magnetic field. And so here I've plotted the band energy versus the quasi-momentum. And these points here, where you have linear energy dispersion on just around the K point, these are the Dirac points. And in the tight binding model, where I only consider nearest neighbor hopping, I can write the Hamiltonian as this two by two matrix, which I can recast in this form. And it is this quantity dotted into the Pauli matrices that sort of brings about this pseudo spin magnetic field picture. And so if you plot the effective magnetic field in momentum space, then what you get is something that looks like this, where the effective field B wraps just one time around the Dirac point. This has a winding number of 1. This is associated with the known pi Berry phase that your system will accrue as it undergoes a trajectory that encloses the Dirac point. Okay, so the pi Berry phase that I mentioned has been measured in several systems. One that I'll point out is this cold atom system here, where effectively they realize a Mach-Zehnder interferometry process by creating a BC, splitting it in such a way, splitting it in a particular way, and enclosing a loop before the interferometry that does or does not include the Dirac point. And that can be seen in this picture here. So in this experiment, and I'm going to say this one more time, but they have a 2-spin component BEC. They can do a process that effectively splits this BEC. They can move it around this Dirac point here, and then they can overlap the atoms again, do their interferometry, and they can detect whether or not there was their loop enclosed the Dirac point. They do this in a honeycomb lattice, just like ours. I'll get into that in a second. They take their 2-spin component BEC. This is a picture of their atoms in momentum space. They apply some spin-dependent force, which sends the atoms in 2 opposite directions. And then they can apply a series of pulses that can reflect the atoms back towards each other, and they can eventually enclose some loop. And they can choose to enclose this point, which is the Dirac point, or they can choose to not enclose it. And so here they plot the phase accrued by their atoms as a function of final quasi-momentum, where you see that there's essentially no phase accrual until they get to K, where the Dirac point is. I shouldn't say there's no phase accrual, but there's a particular kind of phase accrual, a geometric one that's developed when they get to the K point. You see a phase jump of pi, and then you keep going in quasi-momentum, you get to K prime, the other Dirac point, and you see another jump of pi, et cetera, et cetera. But one question we have is, what happens if the winding number was 2? What if you had a singularity that had an associated 2 pi Berry phase? With such an interferometry process, you wouldn't be able to see it, but we think we have a way to be able to see, to tell the difference between 0 or the 2 pi Berry phase associated with a singularity. So not only are there Dirac points, these linear band touching points where the band structure is singular with winding number 1, there are also these quadratic touching points. For example, in the Cogamine lattice, between the 2nd and 3rd band, you have a quadratic touching right at gamma, so at 0 momentum. This has an associated winding number of 2, where if I consider this effective magnetic field pseudospin picture, that effective field wraps around twice as I go around this circle, as opposed to once for the Dirac point. But you actually don't need the Cogamine lattice to look at either of these touching points. In the honeycomb lattice, in the S-band manifold, so the energy bands that are associated with the motion, the ground state motion of particles in the lattice sites, they're just 2 states here, and at K you have your Dirac point. But in the P bands, so the motional states of the atoms are in their next lowest energy state, you have a quadratic touching between your 4th band and what looks like a flat 3rd band for a sufficiently deep lattice right at gamma. Okay, so what might you expect if you did something unusual? By unusual, I mean, instead of considering trajectories where you wrap around the singular point, the Dirac point, in some sort of closed loop, what if you move your system right into it and then turn away at some angle? So imagine that I send my atoms along some trajectory in this direction where I'm in this effective spin down state. I move to the Dirac point and I turn at some angle. And then I have a situation where I have spin down atoms, and all of a sudden, right when I move away from the Dirac point, I have turned on this effective magnetic field that is not aligned with the spin of my atoms. And so I've suddenly turned on a field where my atoms are going to be projected into some superposition of what is spin up and spin down based off of the magnetic field that points at an angle that depends on this angle, the difference in my trajectories. In this picture, this is another way of thinking about the same thing. You might imagine that if theta is 0 in this picture, then if I send atoms along the 1st band, they stay in the 1st band. If I send the atoms along the trajectory theta equals pi, then you might expect to have full population inversion from 1st band to 2nd band. Or if I send the atoms in at if I send the atoms into the Dirac point and then turn at a right angle, this is 90 degrees or 270 degrees, you might expect a even superposition or equally split superposition of atoms in the upper and lower states. And so what you would expect to find is a ground band population that looks like cosine squared of half of this turning angle versus an excited band population that looks like sine squared of half of that turning angle. And this is a situation where the winding number is measurable via your ability to find out which atoms are in which bands. Okay. Similarly, if I instead think about the quadratic touching point, remember the effective field wraps twice around the quadratic touching point. This picture, the picture of what happens when you send atoms along a particular band is similar. At theta equals 0, you might expect no change between 3rd and 4th band. At theta equals pi, you might expect complete population inversion, but then at theta equals pi, again, no population inversion. This is an effect that is measurable, and it's a very noticeable difference between this from what you see with the singular band. So in this picture, you would expect cosine squared of this angle and sine squared of that angle for the ground band population and excited band population. And here's a situation where winding numbers 0 and 2 are distinguishable from each other. Okay. So that is a lot of background from what we're about to try to do, or for me to describe what we've tried to do. Wanted to say how we mentioned the honeycomb lattice. I know I already showed you how we make the Kagamine lattice. Making a honeycomb lattice is even simpler. We only need one set of beams, so just 3 beams. We look at the overlapped region here. We see a potential energy landscape that looks like this, where I've marked the potential minima with these green dots. So this is my honeycomb lattice, and I can span this lattice with these two lattice vectors, A23 and A12. Okay, so in order to do this sort of experiment, we have attempted to do what I described to you before, where we move along some trajectory in momentum space and then we turn at some angle. In order to do this, we developed a technique where we can use feedback control of all of our lasers to translate our lattice. And if we translate our lattice relative to the atoms in the lab frame, in the lattice frame, it looks like the atoms have been transported to or boosted to some quasi-momentum, right? So we can use feedback control, and this is an important point for us, to realize a lattice velocity, VLAT, that takes this form. These are the lattice vectors, and these parameters, F12 and F23, these are some time-dependent quantities that are knobs that we can tune in the lab. And so we can sort of, at our discretion, give the lattice this velocity, whatever we want it to be. And in the lattice, the atom's quasi-momentum is given by minus m times this lattice velocity. And so in doing this, we can give the atoms, using feedback control, whatever quasi-momentum we want in any of these bands that I'm showing. So this is my reduced Brillouin zone scheme for my 2-dimensional honeycomb lattice. We can start the atoms at gamma, for example, 0 momentum, and we can change their quasi-momentum and put it anywhere along this line, go through this line, we can turn at this angle, we can sort of do whatever we want. So in these panels, what I'm showing you is a series of momentum space images of atoms that we've moved to different quasi-momenta along this path. So in this first panel, this is just an momentum space images of atoms at gamma at 0 momentum. This is what we expect from theory. This is what we see. In this panel, I've moved the atoms in quasi-momentum 2/3 of this distance. This is what we expect from momentum space imaging for this distribution. This is what we see. And in this picture, I've moved the atoms right through the Dirac point over into this region. This is what we expect. This is what we see. So we are very confident that we can move the atoms into the quasi-momentum that we want, in the band that we want, in a way that we couldn't do in the method that I described to you for the flat band. So before, we would pulse on a laser and we would give the atoms a kick, but we can only kick in one direction. And this process of trying to do multiple kicks basically can't work. But here, up to some total time of the experiment, we can do arbitrary trajectories in quasi-momentum. So in order to do the measurement that I described to you before, where we touch the Dirac point and move off at some angle, we use this feedback control to move the atoms from gamma to the touching point, to the Dirac point, and then we turn at some angle here. Okay. What I'm showing you are measurements that we call band mapping, where we're able to adiabatically turn off the lattice in a way that maps the atoms that were in different bands in the lattice to different peaks in momentum space that are associated with the group velocity associated with the atoms when they're in the lattice. So what that means is we can do this band mapping process. We can overlay the reduced Brillouin zone scheme picture in the appropriate way. We just need to shift it by the quasi-momentum relative to what corresponds to 0 momentum in the picture. And then we can directly read off which atoms are in which band. We can read off which atoms were in, not which, but how many atoms were in each band. Okay, and so this is an experiment where we move to the Dirac point and we turn at some angle. That angle is given by this expression here, pi over 6 plus an integer n times pi over 4. All right, so we have 8 points here. where we are just going off at not random, but a series of angles from the direct point. We overlay these Berlin zone images. We can extract the band population. There we go. Okay, so this is how we're doing these experiments. This isn't the same data, but it's the same process. Instead of having such large steps, this is a data set where we've stepped by 15 degrees. What I've plotted in the dash, using the dashed lines, is the sine squared and cosine squared theta over 2 dependence that I mentioned to you that I would expect to see. And the circles are our data. So we see that both the blue data, the first band, and the orange data, the second band, they agree pretty well with what we expect. We're investigating where these differences, like why the contrast isn't full, why the orange doesn't quite overlap with this, with the sine squared. And it's not because of interactions, we think. There is a way that adiabaticity does play a role in this experiment. What I've tried to show you is that there's some process that's completely geometry dependent, trajectory dependent. I should say geometry of trajectory dependent, where we get this inner band population inversion. But it turns out that part of how we actually do the measurement is non-adiabatic, and we think that this is why the data doesn't extend all the way up here or all the way down here, for example. This is my last data set. This one is in a very raw form. You know, we've just sort of started to finish this up. But here's another set of experiments where we study both the K and K prime points. So both Dirac points, but K and K prime are the points that are distinct from each other. So we undergo a trajectory that looks like this. We go from gamma to this Dirac point, and we do band mapping at gamma. Or we go from gamma to K prime, and then do band mapping at gamma again. And we can look at a number of trajectories that go between the two extremes. Or even this one that goes from gamma to M to gamma. So effectively doesn't see any interesting band geometry along that trajectory. What I'm plotting in this panel, this plot, is the what I call the band contrast. So this is band 2 population minus band 1 population normalized by the number of atoms. And so for the this red and this green in this plot corresponds to the red green here. So the sort of deeper the red or green color, this is a trajectory that is closer to the Dirac points. And you see that the contrast that you have for the deeper colors, so closer to Dirac points, is more in line with the half, equally split, whereas not equally split, but more in line with the half. Whereas trajectories that are closer to M show that the contrast becomes more and more negative. So as you go through a trajectory that doesn't get near the Dirac points, your contrast is more and more negative, which means that you have more atoms in band 1. So sort of, and then I'm plotting this as a function of time that I take to move through my different quasi-momentum. So this is a proxy for the acceleration of the atom experience. And you see that if you move slowly, then you don't see this population inversion. And sort of independently of how slow you move, when you are investigating the Dirac points, you see population inversion. So this population inversion, it's a result of geometry, I would say. And so this is another way to recast the same data. And this delta is an in-lab unit. This delta parameterizes where we are along this path in momentum. So delta equals 0 is this Dirac point. Delta equals 1 is this Dirac point. I've just taken the data in these 3 different shaded regions and I've averaged them together. And what you see is as I consider trajectories that I've done more and more slowly, you see the contrast or the population inversion change, such that when I go slower, or if I'm along trajectories that are not near the gamma points, the contrast dips, and it dips quite quickly. but only in regions that are far away from the Dirac point. So here's one Dirac point, here's another Dirac point, sort of, again, regardless of my speed, I get this population change that depends on geometry, and it's not some, you know, diabatic, like it's not a process, an inversion process that depends on like how fast I accelerated my atoms. Okay, so I will summarize now. The Kagamine experiment first, we place atoms into the flat third band of the Cogamine lattice. We've seen that interactions renormalize the band structure. And again, this is telling us something important. Think about condensation in flat band. This is something that we want to continue to study. As I mentioned, we also can make a flat band in the honeycomb lattice. If you have a sufficiently deep lattice, the third band, one of the P bands, is flat. But we also hope to see other interaction effects. And then for the Dirac point experiment, you know, we have a new way to probe band singularities, and this is by touching them, and then instead of going in loops around them, we touch them and then we move off at some angle, and we can measure the winding number associated with that band touching point with the projected measurement. This is my band mapping that I mentioned to you. And you know, while this isn't, you know, I think we've come across an interesting physics result, so maybe there's not much reason to talk about a measurement technique, but you might think about whether or not this technique allows us to measure quantum distance or the overall quantum metric, which I think people would say is the most general way to describe the geometric properties of the Hilbert space that's relevant for describing your system. And then, yeah, the next step is to apply this technique to the quadratic touching point. And this will be really special because no one's seen this. And again, the typical way to measure these singularities with cold atoms release is to realize some sort of interferometry process. There's one exception to that, one very important exception to that. But okay, this is the awesome team of people that I work with. Our new postdoc, well, he was a grad student in the group for a long time. He's in the postdoc now. Two really awesome young grad students, my advisor, Dan Stanker, and thank you.
Great, thank you. I guess we go to questions now. Let's open it up for questions.
I have a whole bunch of questions about the experiment. As a condensed matter experimentalist, I'm curious, what temperature do you do these experiments at? How long can you trap? When you load the atoms, how long can you keep them there? Those kinds of just practical things.
Well, sure. Yeah, so the BEC is, there's definitely some shot-to-shot variation in the temperature, but the BEC temperature is 50 to a few hundred nanokelvin. And we can hold the atoms in the lattice for maybe, okay, it really depends on what we're doing. If we have a stationary lattice, we can hold the atoms in a stationary honeycomb lattice for tens of milliseconds before we have too much loss. With these experiments, we can only hold them for like 5 milliseconds or so. I think it's because we have a little bit of lattice shaking. I think we have a little bit of Floquet physics happening, and we don't want it, but there's a little bit of residual shaking maybe of our lattice that might be causing some loss. So I would say, you know, all these measurements that I've described for the band touching point physics, that's all done in less than like 4 milliseconds.
So for each of the points on like your last few graphs, do you do a whole bunch of runs and average them, or is it one run for each point, or how does that work? Yeah,
so for example, so this trajectory, in this data, we've done each one of these trajectories 5 times. And for each of those, we've done them for different acceleration times. So let's see, there's a better way to describe this. The acceleration time refers to how fast I change my quasi-momentum from 0 to this quasi-momentum back to this gamma point. So not only have I done this for all these acceleration times, but I've done each one of them 5 times.
And these are rubidium atoms?
This is rubidium, yeah, it's rubidium-87.
Atoms. Thank you. Yeah.
Actually, I had a quick experimental question also. Maybe this is a good moment to ask it. You mentioned that you might be able to make spatial images of that strange state that you have in the first experiment. What kind of spatial resolution could one hope for?
That is a super important question. So it totally depends on your lattice and not so much your species, but okay, actually, yeah, your lattice and your species, I would say, because different species require different species. We tend to associate with different. We use different lattice light for them, and if the lattice wavelength is different, then the space between sites are different, and so your site to site gap is going to depend on the light that you're using and the atoms, and so that's what's going to place the bound on your what resolution you need. Some people are making quantum gas microscopes. Like there's the one in the Harvard group. There's one at Princeton, I think, in Wasim Baker's group. It's hard to do a quantum gas microscope for our system. In our Cogamine lattice, the lattice spacing is 355 nanometers, and there hasn't yet been a quantum gas microscope that has single site resolution that low. I think the best one can resolve sites that are separated by 500 nanometers, maybe a little bit more. And so it would be really amazing if someone could either figure out how to push past the resolution frontier and use a Cogamine lattice like this to have single site resolution of the sites of the Cogamine lattice, or just make a different kind of Cogamine lattice that is that uses different wavelengths. So for example, I've been thinking about, should I want to do this one day? Maybe instead of using 532 nanometers and 1064 nanometers, you can make a Cogamine lattice with 1550 nanometer light, which is a very, very common wavelength. Lots of really awesome technology there, and half of that. And that would already put you into a regime where you could build a quantum gas microscope, so you can have imaging resolution at a single site. You can't do that. You can't do these wavelengths for rubidium. It wouldn't work because the half wavelength is close to the D2 transition. So you would resonantly scatter them out of the lattice, but there might be a way to figure out how to have single site resolution. But that was kind of a long-winded answer, but yeah.
Oh, that's really interesting. And this is a really interesting experiment too. But maybe what I'll do is I'll let Walter ask the final question, and then we'll end the formal proceedings and go on to informal discussion. So go ahead, Walter.
Okay, yeah, so very nice talk. But, I'm coming from a condensed matter theory perspective, so I'm used to thinking about electrons maybe on these lattices, but you talk about atoms, right? Mm-hmm. And so my first question is, can you do this both with bosons and with electrons? With bosons and with fermions. Can you use atoms that would be fermions?
We can't yet, but we are building that. So in my copious amounts of spare time as a postdoc, I'm also leading the construction of a new experiment where we're going to do ultracold fermionic potassium. So we want to do a lot of these experiments, in particular the flat band stuff with fermions.
I see.
Yeah.
So yeah,
but we don't have any fermions in our lab yet. Okay,
so I often hear it that one of the advantages of AMO physics is that you can tune the interactions, right? And so what I'm wondering, if you think about your boson experiments now, what experimental situations in condensed matter physics could this be like a proxy for, or like an analogy to, so we could understand better the corresponding interactions in a condensed matter system?
Interesting question. So yeah, we have access to these Feshbach resonances that we can build with applied magnetic fields, and we can tune the interactions. So I'm building this experiment, an upgrade that can use fermionic potassium, that's potassium 40, which has a really strong Feshbach resonance. So you can tune the interactions basically to zero, or make them attractive, actually. So negative scattering length you can do. For rubidium 87, the Feshbach resonance is weak, so we basically can't control the interactions very much. Rubidium 85 is harder to use and could be available to us with changing our optics system, but that has a more tunable Feshbach resonance, so you can change the interactions. Regarding the crossover to condensed matter physics, I want to say, I don't know. And this is sort of a open question. Like we're able to control our systems in a way that's a bit different than what traditional condensed matter systems can do, like solid state systems can do.
So I was thinking, like, for example, of excitons. Excitons are an electron and a hole that pair, and it's effectively like a boson. So can I learn about excitons moving on a lattice like that by looking at your system with atoms? And
yeah, so I think that should be the case. So yeah, I have come across some exciton condensation papers. I know that people do even make Cogamine lattices for optical systems. I know that people have even realized Cogamine lattices for acoustic systems. There could be, yeah. So okay, let me. I think the answer to your question, I think what I can say to your question is yes, this should be able to tell other systems that are looking at bosons in flat bands. This should be able to. I think this is some sort of analogy to those systems. Okay. How those systems come about, whether it's a electromagnetic, I shouldn't say that, but like an exciton version of a flat band, or maybe a photonic version or an acoustic version. I think it doesn't matter so much as long as you can engineer some sort of effective interactions. And I know that in the photonic case, I did come across some work recently where people could effectively make what looked like photon interactions in a photonic system. So if you can generate that sort of effect, then I think this totally applies to other kinds of systems.
Thank you.
I have a question.
Could we save that for the informal session now? I think we should probably end the formal session here. But I guess I'll add one reflection, which is I feel like the AMO field has moved far beyond excitons and many other fields. So I think that is part of the answer, that the other fields need to catch up before they can be maybe compared to all of this stuff. In any case, this was a wonderful talk, and thank you so much. And let's move on to informal discussion